Hello and welcome back. Before we leave this packet, I'd like to share two integration tricks with you. These tricks can sometimes make it easier or much easier to integrate. Now the tricks require that you have either an even function or an odd function, so let's review what those mean here. Remember that a function little f of x is even if little f of negative x is equal to little f of x. So if you plug in a negative x or you plug in an x, if the two function values are equal no matter what, then the function is said to be even. And little f of x is odd if when you plug in x and negative x, you get the same function value but just opposite signs. In other words, if f of negative x is equal to negative f of x. So you might recall that some even functions include x squared, or the absolute value of x, or cosine of x. And some odd functions are x, or x cubed, or sine x, or tangent x. Now let's look at the f is even case. If f is even, and you're looking at the integral from negative a to a, this is an important part of it. You have to be going from negative a to a, where a can be anything. So this could be negative 2 to 2, or negative 5 to 5. And here's your f of x inside the integral. Then this is equal to 2 times the integral from 0 to a of f of x dx. The reason for that is if you remember what it means, what it visually means for a function to be even, what it implies, it means that the function on the right side of the y-axis is going to be equal to the mirror image of the function on the left side. So the left and the right sides are mirror images of each other across the y-axis. Now let's say we're looking at the area under that curve from negative a to a. Well, if the curves are just mirror images of each other across the y-axis, then whatever area you have under the curve from 0 to a is going to be the same as the area under the curve from negative a to a, or from negative a to 0. So what you could do is, instead of finding the area under the curve from negative a to a, you can instead find the area under the curve from 0 to a and then multiply your area by 2 to get the full area from negative a to a. And that's exactly what this is stating right here. If f is even, then the area under the curve from negative a to a is just twice the area from 0 to a. Now the second trick is if f is odd. If f is odd and you have the same kinds of limits of integration, so from negative a to a, it could be negative 2 to 2, for example, then this integral is going to be equal to 0. This is what makes this trick make your integrals much easier. As long as they're in this form and you've got an odd function inside, then this is going to be the simplest of all integrals to do. Visually, the reason for that, why we get 0, is this. An odd function would look something like this. If here's the function in the first quadrant, then an odd function would say that any function value you get over here with a positive x value, if you plug in the negative x value, it will have an opposite sign. So it's going to be symmetric about the origin. It'll be as if you took this function, flipped it about the y-axis, and then flipped it about the x-axis. Or you can think rotating it at 180 degrees. But the main thing is you have this symmetry. It's like if you reflected the function across the y-axis and then looked at the mirror image across the x-axis, that's exactly what you would get. So now here, if we're looking at the integral from negative a to a, notice that this area from negative a to 0 and this area from 0 to a are going to be the same but opposite signs. Here you're going to get positive area because the function's above the x-axis, and here you'll have negative area because the function's below the x-axis. And they'll be exactly the same in magnitude, but just opposite signs. So when you add them together, you're going to get 0. Let's use that for example 6. We'll try to figure out if this function is even or odd. Remember, this function that's inside the integral is also called the integrand, in case you ever hear that word. So here's your function inside the integral called the integrand. What we're going to do is try to figure out is that function even or odd by plugging in negative x into the function. That's how you can start out. You can plug in negative x into the function, and then depending on what you get as a result, if you get back to the original function, it's even. If you get back to the negative of the original function, then we've got an odd function on our hands. So let's plug in negative x and see what happens. Here we're going to replace all the x's with negative x's. And those even powers are going to eat the negative in front of the x. So you'll just get x to the fourth minus 4x squared plus 6. Negative 1 to the fourth is 1, and that'll make the coefficient disappear. Negative 1 squared is 1, and so that 1 times the negative 4 will give you negative 4 in front still. So basically you get back the original function. So f is even. And since we're talking about the integral from negative 2 to 2, this is like a negative a to a of this even function, we can instead integrate from 0 to 2 and double that. So this 2 here is not related to this 2 up here. This is twice the area from 0 to 2 of x to the fourth minus 4x squared plus 6 dx. So then what you do is you take twice the antiderivative evaluated from 0 to 2, so this is going to be x to the fifth over 5 minus 4x to the third over 3 plus 6x from 0 to 2. I have a little itch right there, so I had to scratch it. And then we have 2 times, when we plug in the 2, we're going to get 2 to the fifth over 5 minus 4 times 2 to the third over 3, and then plus 6 times 2. When we plug in the 0, we're going to get 0, 0, 0, so we're going to get a minus 0. So eventually when you work all the fractions out, you get 232 over 15. Okay, so that it doesn't really save you a whole lot of time, but at least it saves you from having to plug in a negative 2. Notice that when we plugged in the 0, we just said 0, 0, 0. That was a lot easier than plugging in negative 2, right? So that can help you out, make your integrals a little bit simpler to evaluate. Now example 7, we have the integral from negative pi to pi of sine x. So sine x in this case is our little f, or cute little f. We'll plug in negative x into that function. We get sine negative x. Remember that sine is an odd function. I guess if we recognize that, we would just say, sine's an odd function. Remember, there's a property, there's a trig identity that says sine of negative x is negative sine x. That's kind of a statement that sine x is an odd function. But here we're writing out all the details. And this is the negative of the original function. So you can see that here our function is odd. So we don't even have to find an antiderivative. We know that if we take the integral from negative a to a, so negative pi to pi here, of an odd function, we get 0. No work to be done. We didn't even have to find the antiderivative in that case. So if you run across the integral from negative a to a of an odd function, that's going to save you lots of time if you recognize that trick. One last thing I wanted to mention is if we visualize if we visualize the integral from negative pi to pi of sine x, that's going to look something like this. There's negative pi to pi of sine x, and you can see that this negative area and this positive area are going to perfectly cancel off each other and leave you with a net area of 0. Thanks so much for watching, and see you next time.